A large portion of today's newest research in physics is in the realm of quantum mechanics. It might not seem obvious, but this research has the potential to lead to technological advancements that could affect everyday life. In 2013, a paper was published titled Imaging Topological Edge States in Silicon Photonics. The paper presented research conducted at the Joint Quantum Institute. To understand what was presented, let's lay some groundwork. First, let's talk about topology. Topology is the mathematical study of shapes and spaces, or the study of properties that are preserved under continuous deformations, including stretching and bending, but not tearing or gluing. For example, a coffee cup and a donut actually have the same topology, but as soon as I take a bite, the topology of the donut has changed. No amount of stretching or bending could make it look like a coffee cup anymore, because I've changed the topology of the system. But what does that have to do with physics? Well, a system can be described in many ways: color, size, or shape. A system can also be described based on its topology. Okay, keep that in mind and let's talk about something called the quantum Hall effect, or QHE for short. The QHE is seen when an electron gas is confined to 2 dimensions and placed in a magnetic field. Imagine a cloud with a bunch of negative charges confined to a cookie sheet-like space and brought close to a magnet. This system can be analyzed based on its conductance, or how well the electrons flow through it. Depending on how the electrons are sent into the system, only a few levels of conductance are measured. Imagine having the option to walk on gravel compared to through water, through sand, or through mud. There are varying levels of ease or difficulty there. The cool thing is, the levels of how easily the electrons flow through the material are linked to a topological descriptor. So the topology of the system affects how the electrons flow. There are 2 categories to describe how the electrons behave in the material: bulk states and edge states. Bulk states describe when the electrons occupy most of the material, and any small changes to the system will affect how they flow. Edge states describe when the electrons travel around the outside edge of the system only. These states are robust because they remain the same despite small changes to the input or to the system. Picture a whirlpool that you may have made in a backyard pool. If someone is entering the pool, they can enter in a variety of ways. Depending on how they enter, they may travel through the bulk or the middle of the pool. The path they take in this case will be very dependent on how quickly they're going and in what direction they were pushed. There are many different paths that are possible. But if a person enters the pool so that they end up where the current is strong, they'll travel around the outside edge of the pool. The path they take will be the same for all of the pushes that get them started around the outside edge. And if something like a ladder is in the way of an outside edge, the water will just flow around the ladder and take the person with it. So what does any of this have to do with light? Well, there are little bundles of light called photons. Hafezi and his colleagues designed an optical chip on a material called silicon-on insulator. On the chips are optical resonators, places that photons like to hang out. They were able to design the chip in such a way that the photons act like electrons in a quantum Hall system, or a tuber in a whirlpool. When light is incident on the chip, some input states result in bulk states, just like the wandering whirlpooler, and change a lot depending on the input. But some states looked like the whirlpooler around the edge, and the laser light was observed to only travel around the outside edge of the chip. For this state, small changes to the input didn't change the path at all. They even removed a resonator from the outside edge, just like putting a ladder into the whirlpool, and the light simply traveled around the missing resonator. This is really cool and unique. In fact, it was the first time that this effect was seen experimentally with photons. So, what does this mean for us? Well, as you know, fabrication processes are not perfect. This research could lead to products that still work despite defects to the edge of the system. In addition to that, it could lead to more light and therefore information being sent at a time. This could lead to an increased speed in many technological devices. The study of mechanics and electromagnetism has led to the fields of mechanical and electrical engineering. These fields have greatly affected industry and the world as we know it. Quantum mechanics may seem so far from anything we encounter on a daily basis, but the possibility of very practical applications, such as optical chips robust against fabrication disorders, leads us to believe that quantum engineers may soon join the ranks. So, the next time that you're enjoying your topologically similar cup of coffee and donut, remember, quantum mechanics isn't actually so far out there and may be affecting your life very soon.